Okay, so welcome to your very first lesson in grade 11 physics. And today we need to start by just talking about the difference between something called scalar and vector quantities. And scalar quantities are actually the kinds of measurements that you're already used to in your regular math and science classes. Things that have what we call a magnitude, which is just a value or a number, but there's no direction associated with them. So a lot of the scalars are things that you've heard of before, and there's lots of different examples we could list, but something like speed is an example of a scalar. When we measure distance, that's a scalar as well, and so speed and distance have units like kilometers per hour, or distance could be in kilometers. We also could have time, or maybe volume or mass, and there are many, many others that we could list. But the key here is that, again, they all have some number associated with them, some amount, and then a unit that represents what that amount really means and what that's measuring. But there's still no direction associated with any of that. Now vectors are a little bit different. Vectors often have a lot in common with scalars. In fact, they have a magnitude still and a unit attached to that magnitude, some amount and a unit, but they also have a certain direction that they're pointing in. And so when we talk about speed, when we also know the direction that something is moving in, we don't just talk about its speed, we use a different word and we call it velocity. And velocity is one of the most important vectors that we're going to deal with in this course. Another really important vector is something called displacement. And displacement is a lot like distance. We measure it as a length like we would distance, but it's got a direction associated with it, a certain direction that that distance traveled has gone in. And another very important one, which we'll see a little bit in this unit, but we'll spend a lot of time in our next unit looking at, is force, because we can talk about a certain amount of force, which is going to be measured in something called newtons, but we can also talk about the direction that the force is going in, and that sometimes is just as important to know when we're solving problems and doing some calculations. So again, as your note says, what we should notice is that these quantities or these concepts can often be very similar, but the two different quantities that are similar are classified a little bit differently. And for example, we're going to talk about first distance versus displacement. And an important little bit of notation to know is that when we're writing the symbols for these, when something is a vector, we add a little small arrow on top of it. And we'll see this a lot as we go through questions. So D, as you can see, represents distance, and distance is the scalar version of it, and there's no arrow on top. But we also use a D to represent displacement, but we put a little arrow on top to make sure that we know that it's different from distance. It's the vector version of distance, which we call displacement. And there's even a little bit of a special definition that we're going to have to put on that, which we'll talk about in a moment. So let's look specifically at how we can properly use these quantities, and the most important ones to start with are distance and displacement and speed and velocity, and how they relate to one another. So the example we're going to start with is this cyclist that's completed half a lap of a 400-meter circular track, and we'll compare their vector and scalar quantities. So pretty simple idea, and this is my incredible art skills here. That is our circular track. And using a different color, I will just mark off, this might be the starting point that our person might have, and they are going to go halfway around this circular track, and their finishing point will be up at the top. So when we are first just talking about the distance that they travel, it should be a fairly straightforward calculation, because we're just talking about how much, or what was the length that they moved as they traveled along that path. And so a lot of you could probably already do this, and I'm sure some of you have already solved this in your head. So the distance, which again, we'll just use a D to represent, no arrow on top because it's a scalar quantity, doesn't matter what the direction is. We just take the full 400 meters of track that we had, and if we're only using half of that track or only going around half of it, we can just divide that entire length by 2. And so, of course, that means their distance traveled has been 200 meters. Displacement, though, we need a bit of a slightly different definition for. So first of all, as I've already said, it's got a direction associated with it. And specifically, it's a little bit more detailed than that. Displacement means the straight line distance between the starting point and the finishing point. And of course, that's then going to be a vector quantity. So we won't just figure out how long that straight line distance is. We'll figure out what direction we're moving in if we look just at the straight line that goes from start to finish. And so rather than looking at the path that takes us around the track, the straight line distance is going to take us straight across the diameter of the circle. And so if we want to know that straight line distance, we're actually going to use a little bit of circle geometry. Circle geometry is not going to come up a ton in this course, but it happens to benefit us here. So in this case, our D with a little arrow on top, and you'll see my arrow actually just doesn't even have the bottom part to its arrowhead. It just has a top part sticking out, and that's totally fine. That's what I'm going to use to represent displacement. And it's just, in this case, equal to the diameter of the circle. And that we can find by taking the circumference of the circle and dividing by that special number pi. And so when we do that, that means it's really 400 meters divided by pi. And then we get a number that we need to just round off. It's about 127.3 meters. But in significant digits, I'm going to say approximately, well, we'll always assume at least 2 significant digits, but I'm going to call this about approximately 130 meters. Again, always assume a minimum of at least 2 significant digits. So there's our difference there between distance and displacement. And that straight line distance between start and finish is really important. When we look at speed, well, your speed is just, once again, a scalar quantity. It doesn't matter what direction you're moving in. When we look at speed, we're just going to take the total distance that you covered, which again uses the scalar quantity distance, and divide it by another scalar quantity in time. So we're trying to figure out how much distance did you cover per second or per unit of time. But in this case, we're going to use seconds, and we're going to figure that out. And so in this case, we actually need to add in a bit of information. In a textbook question or on a test, you of course be given all the information at the start. We're just going to make up a little bit of information to finish off this problem. So up top, I'm just going to write that we're going to assume that time, in other words, how long it takes him, is 10 seconds. So now here's a little bit of notation that might be a little confusing for you. Even though we're going to talk about speed, in physics we often still use a v to represent speed, and that v connects with velocity, but if it doesn't have an arrow on top, then it means we're talking about the scalar version of velocity, the version of velocity that doesn't have a unit or a direction associated with it. And so when we have a v with no arrow on top, that really means the speed. And that speed is going to be just distance divided by time. Or in other words, that's 200 meters, excuse me, almost put 400, but that's 200 meters divided by 10 seconds. And right away we can see what's happening with our units. We have meters divided by seconds, and so our unit in the end should reflect those two units coming together and being divided by one another. So the 200 divided by 10 gives us 20. And our units are in meters per second. And so that cyclist was moving incredibly fast, but it just gives us a good idea of an example that we can use in this case. For velocity, it's a very similar idea, and the formula looks very similar. But now I'm going to put a little arrow on that v, because now we're really dealing with the true vector version of velocity. And that's going to be equal to d with a little hat on top. In other words, displacement, the vector version of distance, divided by time. And when we take a vector and divide it by a scalar, which is what we're doing when we do displacement divided by time, a time doesn't have a direction associated with it at all. Time just moves forwards, and we don't really think about it as a direction in this case. And so whatever direction the displacement has, it'll be the same direction as the velocity, which should make some sense. If I'm moving if I'm displacing myself towards the east, then my velocity is moving towards the east. And so specifically, I'm going to go back and reuse the more precise measurement that we got in our original calculation. So I'll use 127.3 meters divided by 10 seconds. And that gives me about 12.73 meters per second, or approximately, I'm going to say about 13 meters per second. But I can also factor in, and just by using my diagram in this case, without any other calculations, I can also put in a final statement to say what direction this is associated with. And so we use square brackets to state our direction. So beside my final answer, and in this case I've run out of room beside, so I can just write it below, I'm going to say that we are moving in the upwards direction. So beside your final value, we just put a little square bracket beside that has our direction. And we'll see this many times throughout this course. So for that question at the bottom of the page about what the speedometer in your car is measuring, I'll let you try and think about that and answer that, and we'll take that up in class. So moving on to how we actually draw these vectors, when we need to draw them in our diagrams, we use arrows, because arrows have a specific direction. And then the length of that arrow, how long it is, will represent the magnitude, or how big of a value that vector has. And then it'll point in its expected direction. If we want to start, though, by drawing these as accurately as possible, we always start by drawing them to scale. And so we need a scale and what we call a direction convention, so we know what direction things are going to point in. And so my direction convention can be something as simple as drawing a little axis to represent north, east, south, and west, and then letting whoever's reading my solution know which direction I'm going to consider to be the positive direction. And so typically the most common thing is that we'll use north to be a positive direction, and then anything that's going south we consider a negative direction. And east we consider a positive direction, and anything that's going to the west could be sort of a backwards or a negative direction. We also need some sort of scale. And so for this first one, example 1, we are in centimeters. And so on your page, it's probably easiest to actually draw your line in centimeters as well. So on your page, I would just use the scale and say, let 1 centimeter on your page represent 1 centimeter of the actual vector that you're trying to represent. When we go over and we do the second example, that's 2.0 meters per second north, now we are representing something in a length. We're drawing a length of a vector, but we're actually not representing a quantity that has length. We're representing a quantity that has a speed, or really a velocity, associated with it. And so we're going to do something a little bit weirder here. You let 1 centimeter equal not 1 meter, but 1 meter per second. So every centimeter that you draw represents 1 meter per second of velocity. And then, when you draw your vector, I'm just going to do mine very roughly, but I encourage you to use a ruler and measure yours out correctly. You'll just draw it to scale. And so I will draw an arrow that is 5 centimeters long and pointing in the eastern direction, as I can clearly see that it is pointing to the east. In the other example, again, now you'll draw something that's 2.0 meters per second, and you'll represent that by, again, using a ruler and measuring it out. It'll be 2.0 centimeters long on your page, but it'll represent 2.0 meters per second and it'll point in the northern direction. So again, these arrows, I really encourage you to draw them out to scale using the proper number of centimeters as you draw them on your page. Now, of course, vectors don't always just point straight to the east or straight to the north. Sometimes they don't point right along a nice axis line. Sometimes they point at an angle. So I'm just going to take a second and erase this stuff, and we'll look at some of those examples at the bottom. So we use a specific notation when we're recording angles or vectors that point on an angle. So if we have something like 4.2 kilometers per hour east, 35 degrees north. What that means is that, first of all, the vector should be essentially 4.2 kilometers long, or we can come up with a scale that maybe has each centimeter represent 1 kilometer, for example. And then if we originally point to the east, we turn 35 degrees north of that. And so it reads kind of like an instruction manual. The first letter tells you the direction to point to first, in this case east. Then the second number tells you how many degrees to turn. And the last letter there tells you what direction to turn towards. So we point east and then turn 35 degrees towards the north. So of course, if we label our different directions, north, south, east, and west, for the first one, it's going to be 3.2 meters. And the scale that I'm going to use for that one is that 1 centimeter on my picture is going to represent 1 meter that we are trying to draw from that real-life vector. And it is west 25 degrees east, or sorry, west 25 degrees south. So if I point directly west to start with, and then turn 25 degrees towards the south, that's not a vector arrow I'm drawing right now, that's just curving and trying to represent where my angle is turning. The actual vector that I draw is going to point in this direction. And again, in your case, I'd like you to really measure and use a ruler so that that is 3.2 centimeters long, so that it represents 3.2 meters. And now this angle in here will, of course, be our 25 degrees. And this is our 3.2 meters that we're representing. I'm going to let you try the last two, and then we'll take those two up in class.